Good afternoon. My name is David Delgado, and I'm a graduate student here at Northwestern in the Materials Science and Engineering Department. And I'm here today to talk to you about my research, which involves making soft stuff stronger, or understanding thin film composites. Now, soft materials are all around us. They're in our Band-Aids, our sports equipment, and more specifically to my research, rubber. Now, one way that scientists are making soft stuff stronger is in car tires. They have to be durable, yet flexible to retain traction with the road and ultimately keep us safe in our automobiles. Now, one byproduct of tires is that we as Americans throw out 300 million tires a year. And due to the chemical makeup of tires, they can't be recycled. And as a result, some trash heaps resort to burning them, which can cause toxic fumes for the environment and have a severe impact on us as humans. So one of the questions we are looking at is how can we make consumer products that are just as strong but use less material? Now, you may remember your water bottle cap a few years ago suddenly becoming half its size. And this is an example of the water bottle company making consumer products that are just as strong but use less material to have less of an environmental impact. Now, this brings me to the crux of my research, which involves studying thin film composites. Now, to help you understand this, I'd like to break down this phrase into two sections, beginning with the term composites. Now, when I was 8 years old, I hated spaghetti. Couldn't stand it, the texture, the taste, whatever it was. Drove my mom crazy, unless she added meatballs. It made one of my favorite dishes, spaghetti and meatballs. And what's key here is that this is mixing two different foods or two different materials to get a better material or a better tasting food, at least for 8-year-old David. Now, I as a scientist can do the same sort of thing in the lab. I can take rubber, or spaghetti in the previous analogy, mix in small bits of carbon, or meatballs, and get spaghetti and meatballs, or what we call composite materials. Now, I'd like to draw your attention to the fact that how small are these small bits of carbon. And do so, I'd like to introduce the concept of nanometers. Now, Rachel touched upon this at the beginning of our symposium. I'd like to reintroduce it. Now, if you thought about the width of a human hair, you could fit about 70,000 what are called nanometers across it. And I work with something called nanoparticles. So these small bits of carbon are a few nanometers across. This is a high-powered microscope image of a cluster of nanoparticles together, with this red circle being around a single nanoparticle. Now, what's amazing is that I can mix these small bits of carbon into rubber and get these super materials. Now, this is an example of some of my research. And as you can see, the y-axis has the strength of the material, and the x-axis has the number of particles in terms of volume. So as you can see, as I increase the amount of nanoparticles I put into my rubber, it increases the strength. Now, this brings me to the second part of that phrase, or thin films. Now, we as scientists have discovered that the same material can have dramatically different properties depending upon how thick it is. For example, a piece of rubber that's a few inches thick has incredibly different properties than the same piece of rubber only a few hundred nanometers thick. Thus, we can combine these two concepts and create thin film composites that have extraordinary and exotic properties that we can use as scientists. However, one issue that we are facing in lab is that the traditional testing methods of these sorts of materials do not work. They require giant samples. Now, to give you sort of an analogy, Sam talked about using Kepler as a telescope to study these giant planets and these giant universes. But you wouldn't use that same telescope to study the size of your foot. You'd use one of those like weird triangle-shaped things you find at shoe stores. So the question we're looking at is that we need to have the right instruments to study these thin film composites. So in my laboratory, we use what's called a quartz crystal microbalance, where we take a very special crystal, where if you apply a current to that crystal, it's going to form. Now you can imagine that the current direction is going from the blue negative to the red positive. And we can exploit this phenomena by switching the direction of the current and deforming the crystal in the opposite way. And in the lab, we alternate the current between forwards and backwards and get an oscillation, which we call a frequency. And you can measure this frequency. And so what we do is we take a bare crystal and we measure the frequency. We'll then cast a thin film composite on top of that crystal, effectively changing how much it oscillates or the frequency. We'll take that change in frequency, we'll do some tricky math, and we were able to gain materials properties that gave us good insight into these wonder materials. So in summary, I use thin film composites to make consumer products that are just as strong but use less material to have less of environmental impact. Thus, we can go from this to a greener future. Thank you.